So these are the first two questions from the Step 3 Algebra Support Booklet. There's a question about a recurrence relation, some functions, and then a question about trig. Let's do the recurrence relation first. So firstly, we're going to do an induction to show this thing here, where f of x is this thing. So we put it as 0. We're going to ignore this second half of the question. Sorry, we're going to put it as 1, obviously. Ignore the second half of the question for now. Put it as 1 into here, and we end up obviously with just this, just a 1 there, a 0 there, a 2 there. And now that, just by definition, is what they gave you f of x is. So it's true for n equals 1. And we'll just write down, I should have written down true for n equals 1. Now we're going to assume it's true for n equals k. So we've put in k's into here, up here, k minus 1, k plus 1. And we're just going to assume that's equal to f of x, where f of x is still this thing, I guess. And now, okay, well, obviously now we need to see what happens for k plus 1. This is just usual induction things. So we put in k plus 1s. And now what do we do with this? Well, we need to desperately use the assumption step at some point, which doesn't have k plus 2s in it. So let's get rid of the k plus 2. And what's the only way we could do that? Well, using the original recurrence relation up here. We haven't actually even used it yet. I'm going to rearrange this for tn plus 1. And then if I pretend this is a k plus 2, that becomes a k plus 1, and that becomes a k. So let's replace like that. Now, I've got down to k plus 1s and k's, which is good. But there's an x here, right? Which is not going to work for the assumption step at all. So how do we get rid of this x here? Well, we notice it's taking away. So what if we could introduce another one to cancel with it? And this takes a bit of trial and error, I guess, as well. But if you replace this k plus this tk plus 1, or one of them, because there's two of them here, replace one of them again with this step up here, then you notice that this term here, when expanded, beautifully cancels with this one here, which is brilliant, and you just end up straight away down to f of x by the assumption steps. That's just a really nice little step there. Takes a few seconds to come up with it, to think of it, but that's all what step questions are about, isn't it? Just sitting here and trying to... I tried a few different things there before I stumbled on that thing to cancel it out. And that's just how it goes. That's just how it goes in step questions. You're given lots of time, so you just need to think of lots of things you can do. Of course, you write down the final line, which you always do in induction questions, and you're done. Now in the case f of x equals 0. So now this is 0, so we can set this to be 0, and that's true for all n, remember, because we just proved that. And in this case, f of x equals 0, so it's still fine. Now we need to, it's given us this thing about r of x, where it's some kind of fraction between t1 and t0 of x. So, well, okay, I could create a fraction a bit like this if I moved these two terms to the other side, and then sort of did a cross divide by tn, divide by tn minus 1, and we create a fraction that looks a little bit like r of x. So that seems interesting. But then we stop and we think about this for a second, and we say, okay, well, if this is equal to this, then surely this must be equal to this, right? It's the same line, just everything lowered by 1, which must be true because the whole thing is true for all values of n. So this must be true. And then we can just keep going down the line. It must be true all the way down to t1, t0. Must be the same as t2, t1 over t1 because of this original line here, where n would just be 1 in that case. Like, it's true for the entire line, which is interesting. So they're all equal to r of x. So that's kind of cool. It's not actually very helpful at the moment. And this is where we need to put our thinking caps on and just create this this thing that, I mean, it's the next step is, I'm waffling because the next step is very hard to think of unless you just have lots of time. And again, that's what step questions are for, right? You have lots of time. What are we going to do with this? Well, look at these fractions here. A really nice trick you can also play with fractions like this is if you were to times them all together, literally everything would cancel except for the uttermost term up here and the bottommost term down there. So I think we can say something along the line of Tn is equal to all of the fractions multiplied together, except for this one would still exist, which is great because that's supposed to be Tn in the first place. And this one would still exist. So I can get rid of that by timesing by this, like that. And this is a true statement, right? Because of this telescoping cancelling idea where everything just cancels in the middle. And we're just left with this, and then that one cancels that one for us. But of course, all of these things, as we said in the previous line, they're all equal to r of x, every single one of them. So therefore, this is telling us that Tn of x is equal to r of x times r of x times r of x, all the way down, times t0 of x. So it's r of x to the power n, because there are n of these from 1 here to n there, times t0 of x. And this seems like a useful statement. I'm going to write it with n plus 1, and n minus 1, because, well, okay, this kind of useful, but what do you do with it? What do you do with it now? Well, what's the only part of this entire thing up here that we haven't used for this second part of the question yet? We used this right at the start where we set f of x equal to 0. We used this whole r of x business. So that was done. F of x itself is equal to 0, so that doesn't matter. We haven't used this yet. Is it possible that we can just throw this into here and that's the ticket? So let's try that. Let's throw it into here. And again, you've got lots of time in a step question to think that maybe this is the thing to do. And at this point, you notice, everything has a t0 of x in it. They've told me t0 of x is assumed to be non-zero. They're giving me the permission slip to divide this by t0 of x. I know I'm on the right tracks now because they told us earlier that, this is something you might want to think about doing at some point. So we know we're on the right tracks now. We can divide by that. And then the next thing we think is, well, okay, this is true for all values of n. Our proof was true for, we inducted it, it's true for all values of n. The whole thing is going to be true for all values of n. All of these equations here, true for all values of n. So now we can just set n to be any value that we like that we think is easiest. And I think the value that I like to that would make this the easiest is n equals 1, because that would make rx squared minus 2rx plus 1, because to the power 0 is 1. And this is just a quadratic equation. So I think I'm pretty much done. This is the same as y squared minus 2xy plus 1 equals 0. Coefficients a is 1, b is minus 2x, and c is 1. Just use the quadratic formula if you want to. R of x equals this thing here. It's got x's in it, which is fantastic because it's supposed to have x's in it. So, okay, we just throw this into the quadratic formula. Minus 2x is just positive 2x. The minus here doesn't matter because we're going to square it anyway. We end up with this. Factorize out the 4, root it down to a 2, cancel the 2's. And you end up with this expression for r of x, which is the whole question done. But it was a really fun little question. Cool. Anyway, we'll do the next question as well because otherwise this video won't be very long. So the next question here, I'll try and do them in twos, is 2003 step 3 question 6. So show this thing here. Well, first, is it easier to go left to right or right to left? Far easier to go right to left because we can just use the compound formulas here. This one goes sine cos, and then this one sine cos, but minus sine cos because of this minus here. These things immediately cancel, so you just end up with 2 lots of exactly the thing they wanted, which is the left-hand side. So nice and easy. Hence, or otherwise, well, we're certainly going to do hence. Find all the solutions to this thing here. Now, we just need to sit here, put our thinking caps on, and realize how is this thing here relevant to this thing here? Well, this thing has a bunch of causes. The only cos in this first line is this one here, and it's times by a 2 sine a half theta. So let's do that. Let's just times this equation by 2 sine a half theta, and just put 2 sine a half theta in front of every single one of these causes like this. Because now I can replace individually all of these with this line here. Maybe this is a terrible idea, maybe it's not. That's the whole point of step, is that we're just going to try it and see what happens. Now, I should mention at this point, because we've times by this is now going to be true whenever 2 sine of a half theta equals 0, which it wasn't before necessarily. So we're going to have to deal with that at the end. But I'll just put a reminder there to remind me to actually deal with it. But for now, let's plow on. Replace this with this object here, where r is just going to become a. And then replace this one, r is going to be a plus 1 this time. So I'm replacing it with a plus 1's. Just into both of those 2 sine equations there. Hopefully you can see what I've done. And then get all the way to the line, replace r with b minus 2's, and then replace r with b minus 1's. And now notice that this is a plus a half. So is that. That's a plus a half. And that's a minus and that's a plus. So these two things cancel. So very similar to the previous question, we're going to end up with lots of cancelling things happening here. Anything else cancel here? Well, this b minus 1.5. And then there's a b minus 1.5 there. So that cancels as well. One's a positive, one's a negative. I wasn't really very convinced about this, so I decided to write out the term after this, which is the a plus 2 terms. And now here's an a plus 1.5, which cancels with this one, so that's great. And I'm pretty convinced that one is now going to go with the a plus 3 minus half term. Seems like it will. That one's going to remain, though, so this one doesn't seem like it has any buddies. But this one will go away if I bother to write down the next term after this. b minus 3 terms I wrote down as well. Now this is b minus 2.5. Which is the same as this, 1 positive, 1 negative, so those go away as well. And this one I think would go away with the minus 4 plus a half term, which would come before this one, so that one's going to go away as well. But this one here doesn't look like it has anything to cancel with. b minus a half is essentially what it is. And so the only 2 terms we're left with is these 2, and that equals 0. So I think we're down to here. Now, when they ask this question, you don't get a step formula booklet anymore, I don't think, unless I'm mistaken. But when they asked this question, you did. And in the formula booklet was this expression here. or all of these things here. Now, you might recognize this section because, of course, you use these two all the time. You barely ever use this, and then you like never use these. Everyone always questions why they're even there. Well, they're very useful right now. Sine of something minus sine of something else. We can use this as 2 cos of the average between the two, sine of the difference over 2 of the two things. So just putting in b plus a half plus a minus half, and then b minus half minus a minus half with the cos and the sine. I'm just using this formula here in here. And yeah, I maybe now that they don't give you a formula book, they would have given you this expression in the question as like a hint. You think about using this at some point. I don't know. I don't write step papers, so I'm not sure. But anyway, this seems okay. We simplify it down, and now, of course, you've got 2 times this cos times this sine equals 0. So either the cos or the sine is 0, and we're into the home straight of the question now. Now, remember that thing I said way earlier about this? We're about to deal with that. But let's first do the causes. Of course, cos is 0 at pi over 2 and 3 pi over 2 and a bunch of other places, I guess. But we could more succinctly write this as, because we've got odd numbers up here all over 2s, it's just 2k plus 1 over 2 where k is an integer. I can't figure out how to write the integer symbol in PowerPoint, so I just wrote integers. I hope that's okay. But anyway, that's one of our solutions. And then, of course, we could cancel the 2s because we want theta equals, right? We could cancel the 2s and divide by b plus a minus 1, and we end up with this here. And now over here, same kind of thing. But of course, sine is 0 at 0 and pi and 2 pi and so on. So it's just a k pi where k is some integer. Now we can times by 2 divided by b minus a, except at this point, we just need to go back up to here for a second and say, okay, well, we invented solutions wherever sine of a half theta was 0. Now that happens at a half theta equals k pi. So theta equals 2k pi or 2m pi. I decided to write here. So basically, it's all the even powers of pi or numbers of pi, 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi, I guess, as well. So how do we eliminate those from this list here, right? This list does contain some of those, I'm sure. How do we eliminate them? Well, what we could say is that, like, we could say, well, let's just find a case where it should work. So if k was a minus b, of course, you'd have a minus b on the top cancels a minus b on the bottom, and theta equals 2 pi, but that was an invented solution, right? Not a real one. That was the one that we got by timesing the whole thing by sine of half theta, which we needed to do, but created those false solutions. So, okay, that's not a solution. We can't have that. But likewise, if it was 2 lots of that, we couldn't have that either, because then you'd have 4 pi after the a minus b is cancelled. So basically, k can be any integer here, as we said before, but it can't be a multiple of a minus b, where that multiple is some other integer, I guess. And that there's probably smarter ways of writing it, but that's what I decided to go with after a bit of trial and error and figuring it out. Anyway, thank you so much for watching, and I'll see you for some more step questions next time.